Before our world of green continents and blue oceans, there was another Earth, a planet draped in white, locked in a silence that spanned millennia. This was not a sudden catastrophe, but a slow, creeping transformation. A subtle shift in the planet's tilt, a change in the chemistry of the air, and the Great Chill began. Mile-high sheets of ice advanced from the poles, grinding continents under their immense weight, carving valleys and forging mountains. Life did not surrender. It adapted, endured, and evolved. Colossal beasts with shaggy coats roamed frozen plains, and a new, resourceful primate stood upright to face the cold. This is the story of the Great Ice Ages, a time when our planet became an alien world of ice and frost. It's a story not just of a frozen past, but of the powerful, cyclical forces that continue to shape our world today, reminding us that the Earth we know is merely a fleeting moment in geological time. Imagine a world without ice, not a single polar cap, not a solitary mountain glacier. This is not science fiction. This was the reality of our planet for millions of years. Before the Great Cold descended, Earth was a greenhouse world, a planet of stunning warmth and abundance. During periods like the Eocene Epoch, some 50 million years ago, the global average temperature was as much as 14 degrees Celsius higher than it is today. The difference between the equator and the poles was minimal, creating a stable, balmy climate that stretched from one end of the globe to the other. Evidence of this lost paradise is etched into the geological record. In the high Canadian Arctic, where today only hardy tundra vegetation survives, scientists have unearthed the fossilized remains of massive redwood-like trees, turtles, and even alligator relatives. Antarctica, the continent we now associate with the most extreme cold on the planet, was a temperate rainforest. Its shores were lined with lush beech forests, and its interior supported a diverse ecosystem of plants and early mammals. The engine driving this global hothouse was the atmosphere itself, which was rich in carbon dioxide, at levels far exceeding anything seen in modern times. This potent greenhouse gas trapped the sun's heat, wrapping the planet in a warm blanket and preventing the formation of permanent ice. Sea levels were over 70 meters higher than they are today, inundating the continents and creating vast, shallow inland seas that teemed with life. This was a planet defined by water and warmth, a world where life flourished in places we now consider inhospitable. It was a stable state that lasted for eons, a testament to the planet's capacity for profound climatic diversity. But the Earth is a dynamic system, and nothing, not even a planetary climate, remains the same forever. Deep forces, both within the planet and far beyond it, were beginning to stir. The very foundations of this warm world were about to be challenged by a series of subtle yet relentless changes. How could such a vibrant, green world transform into a frozen sphere? What colossal mechanisms could overpower this entrenched warmth and plunge the Earth into an age of ice that would reshape its very surface? The answer lies not in a single cataclysm, but in a slow, perfect storm of cosmic rhythms and terrestrial upheavals. The great cycles of ice on Earth are not random. They arrive and depart with a predictable, rhythmic pulse, a beat set not by forces on our world, but by a grand celestial dance. For centuries, the cause of these recurring ice ages was one of geology's greatest mysteries. The answer would come from a Serbian mathematician named Milankovitch, who spent decades performing meticulous calculations long before the age of computers. He proposed a revolutionary idea, that subtle, long-term variations in Earth's orbit around the Sun act as a cosmic pacemaker, initiating the planet's shifts in and out of glacial periods. Milankovitch identified three primary orbital cycles. The first is eccentricity, the changing shape of Earth's orbit. Over a period of about 100,000 years, our path around the Sun shifts from being nearly circular to slightly more elliptical. This alters the total amount of solar radiation the Earth receives throughout the year. The second cycle is axial tilt, or obliquity. Over 41,000 years, the tilt of our planet's axis rocks back and forth between about 22.1 and 24.5 degrees. A greater tilt means more extreme seasons, hotter summers, and colder winters. A lesser tilt leads to milder seasons, with cooler summers and less severe winters. The final, most complex motion is precession, the slow wobble of Earth's axis, much like a spinning top. This 26,000-year cycle determines which hemisphere is pointed toward the Sun when the Earth is at its closest point in its orbit, effectively changing the timing of the seasons. Milankovitch theorized that these three cycles overlap and combine in complex ways. The key, he argued, was not colder winters, but cooler summers in the northern hemisphere, where most of the planet's landmass is located. If summers are not warm enough to melt the previous winter's snow, it begins to accumulate. Year after year, layer upon layer, the snow builds, compacting into ice. For decades, his theory was debated and largely dismissed. But in the 1970s, deep-sea sediment cores provided the proof. By analyzing the chemical signatures left by ancient marine organisms, scientists could reconstruct past global temperatures and ice volume, and the data was a stunning match for the rhythm predicted by Milankovitch's cycles. The cosmic pacemaker was real. Yet, these orbital variations are subtle. They change the sun's energy by only a small fraction. On their own, they are not powerful enough to encase the globe in ice. They are merely the trigger. Something else, a set of conditions on Earth itself, had to be ready to amplify their gentle push into a planetary deep freeze. While the cosmic pacemaker set the tempo for the ice ages, the stage was set by a force far more powerful and patient, the slow, inexorable drift of the continents themselves. The map of the world we know today is a mere snapshot in geological time. For the planet to become cold enough for ice to take hold, the very arrangement of its lands and seas had to change. The theory of plate tectonics reveals a planetary surface in constant motion, a slow dance that reconfigures oceans and builds mountains over millions of years. Two key events in this continental ballet were critical in priming the Earth for a great cooling. The first was the isolation of Antarctica. Around 34 million years ago, the supercontinent of Gondwana finally broke apart. South America and Australia drifted north, leaving Antarctica stranded over the South Pole. This opened up two critical oceanic gateways, the Drake Passage and the Tasman Gateway. With these passages clear, a powerful new ocean current was born, the Antarctic Circumpolar Current. This massive circular flow of cold water endlessly circled the southern continent, acting as a thermal barrier. It prevented warm subtropical waters from reaching Antarctica's shores, effectively putting the continent into a deep freeze. A vast ice sheet began to grow, locking away water and creating the polar cap that defines our planet today. The second major event was a continental collision on the other side of the world. The Indian subcontinent, having drifted north for millions of years, slammed into Asia. The result was the monumental uplift of the Himalayan mountains and the vast Tibetan plateau. This geological upheaval had a profound atmospheric consequence. The immense new mountain ranges exposed trillions of tons of fresh, unweathered rock to the elements. As rain, containing dissolved carbon dioxide, fell on this rock, a chemical reaction known as silicate weathering occurred, pulling CO2 out of the atmosphere and eventually locking it away on the ocean floor. Over millions of years, this natural process acted as a global thermostat, gradually lowering the concentration of greenhouse gases and weakening the planet's ability to retain heat. The final piece of the puzzle fell into place more recently, around 3 million years ago, when volcanic activity formed the Isthmus of Panama, connecting North and South America. This closed the gateway between the Atlantic and Pacific Oceans, fundamentally rerouting global ocean circulation. It strengthened the Gulf Stream, which now ferried warm, moist water far into the North Atlantic. This moisture was the essential ingredient, the fuel that would soon fall as immense quantities of snow over North America and Europe. The world was now perfectly arranged. The continents were in position. The atmosphere was thinned of its heat-trapping gases. The cosmic pacemaker was ticking, its cycles aligning. Earth was holding its breath, poised on the brink of a new, colder reality. It begins not with a cataclysm, but with a single snowflake, then another, and another. A snowflake that falls in the highlands of Scandinavia or the vast expanse of northern Canada and, for the first time in millennia, survives the summer sun. This is the moment the world tips. The cosmic and tectonic preparations are complete. A Milankovitch cycle has aligned to deliver a series of cooler-than-average summers to the northern hemisphere. Winters are no colder than before, but the gentle warmth of summer is no longer enough to melt the accumulated snow. What begins as a persistent snow patch year after year grows deeper and wider. Under the immense pressure of its own weight, the buried layers of snow undergo a transformation. The delicate crystals are compressed, air is squeezed out, and they recrystallize into dense, interlocking grains of ice. This is no longer snow, it is firn, the intermediate stage on the way to becoming true glacial ice. As these nascent ice fields expand, they trigger the most powerful amplifier in Earth's climate system, the albedo effect. Fresh snow and ice are brilliant white, reflecting up to 90% of the sun's energy back into space. The dark forests, tundra, and rock they cover once absorbed that energy, warming the region. Now, that heat is rejected. This creates a powerful positive feedback loop. More ice leads to more reflection, which leads to more cooling. This regional cooling allows the ice to expand even further, covering more ground and reflecting even more sunlight. It is a runaway process, a vicious cycle of cold. A small initial change, prompted by a distant orbital wobble, is now being magnified on a planetary scale. The planet's thermostat is broken, stuck in the on position for cooling. Across the northern landmasses, small mountain glaciers merge, flowing down valleys to form larger ice caps. These caps coalesce into vast, continent-spanning ice sheets. In North America, the Laurentide ice sheet begins its growth, centered over Hudson Bay. In Europe, the Scandinavian ice sheet forms over the mountains of Norway and Sweden. These are not just static masses of ice, they are dynamic systems, accumulating snow in their centers and slowly beginning to spread outwards under their own colossal weight. The Great Freeze is no longer a potential future. It is an active, growing reality. The world is being remade, one snowflake at a time. The ice is awakening, and it is beginning to move. A new geological force has been unleashed upon the planet, a slow-moving but unstoppable power that will grind continents and command the oceans. It moves with a power that defies imagination. At its heart, a glacier is a river of ice. Under the crushing weight of a mile-thick ice sheet, the ice at its base behaves like a plastic, deforming and flowing outward from the center of accumulation. This is the march of the glaciers, a relentless advance that reshapes the very bones of the Earth. These continental ice sheets were the greatest bulldozers the world has ever seen. As they advanced, they became armed with the rock and debris they scraped from the ground beneath. This material, embedded in the base of the ice, turned the glaciers into colossal sheets of sandpaper, grinding, scouring, and polishing the bedrock over which they passed. They straightened river valleys, carving them into the deep, characteristic U-shapes we see today. They gouged out immense basins that would later fill with water to become the Great Lakes of North America. Along coastlines, they excavated deep fjords, leaving behind the spectacular landscapes of Norway, Greenland, and Alaska. The sheer scale of this transformation is staggering. At its peak during the last glacial maximum, around 20,000 years ago, the Laurentide ice sheet covered nearly all of Canada and stretched as far south as New York City and St. Louis. The Scandinavian ice sheet blanketed Britain, Ireland, and Northern Europe, reaching deep into Russia. Together, these and other glaciers held so much of the world's water that global sea levels fell by more than 120 meters. This dramatic drop exposed vast new areas of land. A wide bridge of land, known as Beringia, connected Siberia and Alaska, creating a highway for the migration of animals and, eventually, humans into the Americas. Britain was not an island, but a peninsula of northern Europe. The world of the Ice Age was colder, but it was also profoundly drier and windier. The massive ice sheets acted as weather generators, creating persistent high-pressure systems that deflected storms and altered atmospheric circulation patterns. The great forests of the north were replaced by a vast, treeless steppe tundra, a cold prairie that supported herds of mammoths, woolly rhinos, and bison. This was the planet at its icy zenith, a world sculpted and dominated by the power of the glaciers. They had reached their maximum extent, covering almost a third of the Earth's land surface. But the same cosmic pacemaker that had summoned the cold was still ticking. The Earth's orbit continued its slow, predictable dance, and a new signal was about to be sent, one not of cold, but of warmth. The great thaw was coming. In the popular imagination, the Ice Age world is a sterile, empty expanse of white, a frozen desert, hostile to all but the most colossal forms of life. But this perception masks a deeper truth. The cryosphere, the realm of frozen water, was not a void. It was a new kind of biosphere, teeming with organisms that evolved extraordinary solutions to an existential challenge. Life, in its relentless drive to persist, found a way. Beneath the surface of the great ice sheets, in the darkness of subglacial lakes, scientists have discovered entire ecosystems. Cut off from the sun for millennia, microbes here do not rely on photosynthesis. Instead, they perform chemosynthesis, drawing energy from minerals in the rock itself. These are some of the most isolated life forms on Earth, a testament to biology's incredible adaptability. On the windswept surfaces of the tundra, a different kind of life took hold. This was not a landscape of towering trees, but of resilient, ground-hugging plants. Mosses, lichens, hardy grasses, and dwarf shrubs formed a living carpet across the permafrost. To survive, they developed remarkable biochemical defenses. Many produced cryoprotectants, natural antifreeze compounds like glycerol, and specific proteins, which prevented ice crystals from forming inside their cells and rupturing them. Their growth cycle was a frantic race against time, compressing an entire year's activity into the few short weeks of the pale summer sun. Even the insect world adapted. The woolly bear caterpillar, for example, could survive being frozen solid. It would thaw in the spring and continue feeding, repeating this cycle for several years before finally pupating. These small, tenacious creatures formed the base of a complex food web. They sustained birds, small mammals, and rodents, which in turn became prey for larger predators. And in certain pockets of the globe, known as refugia, conditions remained milder. These ice-free oases, often in mountain valleys or coastal regions, became vital sanctuaries. Here, species that could not adapt to the extreme cold found shelter, preserving genetic diversity and serving as biological reservoirs from which life would later re-emerge to reclaim the land. The cryosphere was a world defined by its limits, yet life pushed against those boundaries with astonishing ingenuity. It proved that even in a world of ice, The spark of existence could not be extinguished. It simply learned to burn in a different way, creating a foundation for the giants that were to come. The Ice Age was a world built on a different scale. The constant cold and vast open landscapes favored size as a key to survival, triggering an evolutionary arms race that produced some of the most magnificent creatures in Earth's history. This was the reign of the megafauna. Towering above all others was the woolly mammoth, the undisputed icon of the era. Covered in a thick coat of shaggy hair with a dense undercoat for insulation, it was perfectly engineered for the cold. A thick layer of fat provided further protection and energy reserves. Its enormous, curved tusks were not just for defense, they were essential tools, used to sweep away snow to uncover the frozen grasses beneath. Moving in great herds, their footsteps thundered across the plains, shaping the very environment they inhabited. Sharing this landscape was the woolly rhinoceros, a formidable and solitary grazer. Lower to the ground than a mammoth but immensely powerful, its defining feature was a massive keratin horn on its snout, used to clear snow and defend its territory. Its shaggy coat and stocky build were classic adaptations to the frigid climate, allowing it to thrive on the tough vegetation of the steppe. But this world was not just populated by colossal herbivores. Apex predators evolved alongside them, growing to immense sizes to tackle such formidable prey. The cave lion, up to 25% larger than its modern African counterpart, was a master hunter of the open plains. It likely hunted in groups to bring down large animals like horses, reindeer, and young mammoths. Its rival was the saber-toothed cat, Smilodon. This was not a creature of speed, but of ambush and power. Its famous canines were not for stabbing, but for delivering a precise, shearing bite to the soft tissues of its immobilized prey. These giants, from the giant ground sloth in the Americas to the enormous cave bears of Eurasia, were the product of unique evolutionary pressures. Larger bodies retain heat more effectively, a principle known as Bergmann's rule. The vast, productive grasslands provided enough food to sustain their massive bulk, and their sheer size offered protection from most predators. For thousands of years, these titans were the undisputed masters of the frozen planet, their forms perfectly sculpted by the forces of the Ice Age. They were the kings and queens of a world that seemed permanent, but they were not alone. A new force was rising, a creature whose strength was not in its muscle, but in its mind. Into this world of ice and giants walked a seemingly fragile creature. Lacking thick fur, immense size, or formidable claws, early humans appeared ill-equipped for the brutal realities of the Pleistocene. Yet they would not only survive, they would ultimately thrive, thanks to their most powerful adaptation, a uniquely cooperative and inventive mind. The first humans to truly conquer the cold were the Neanderthals. For over 200,000 years, they made Ice Age Europe and Asia their home. Their bodies were compact and robust, a physical adaptation to conserve heat. Their large nasal cavities may have helped to warm and humidify the frigid, dry air they breathed, but their true strength lay in their intelligence. They were skilled hunters, working in coordinated groups to confront bison, horses, and even woolly rhinos. They crafted sophisticated stone tools and understood their environment intimately, tracking the seasonal migrations of animal herds. Evidence from their campsites suggests they cared for the infirm and the elderly, a sign of complex social bonds that were crucial for group survival. Then, a new people arrived, Homo sapiens. Migrating out of Africa, they were more slenderly built than the Neanderthals, a trait less suited to the cold. But they possessed other advantages. They formed larger social networks, allowing for the exchange of information, resources, and mates over vast distances. This network acted as a safety net. If one group faced hardship, others could help. Survival in the Ice Age was a relentless challenge. Shelter was the first priority. Caves provided natural protection, but where none existed, humans built their own structures. Some used the massive bones and tusks of mammoths as a framework, covering it with animal hides to create sturdy, insulated dwellings. Clothing was just as critical. Using sharp stone scrapers to clean hides and bone awls to punch holes, they fashioned layered, well-fitted garments that trapped body heat and kept them dry. Hunting these giant beasts was a high-risk, high-reward endeavor. It required intricate planning, communication, and courage. A successful hunt meant a wealth of resources: meat for food, fat for fuel, hides for clothing and shelter, and bones for tools and structures. It was the foundation of their entire existence, a testament to their growing mastery over a world that should have been their undoing. They were not just enduring the cold, they were conquering it through ingenuity, cooperation, and sheer resilience. Human resilience was not just a matter of spirit, it was forged in fire and stone. The ability to create and innovate, to transform the raw materials of the natural world into tools for survival, marked the single greatest leap in humanity's journey through the Ice Age. While early hominins had used simple stone choppers for over 1 million years, the cognitive and technological explosion of the later Pleistocene was revolutionary. Neanderthals perfected the Mousterian technique, a sophisticated method of preparing a stone core to strike off a perfectly shaped flake with a single blow. This was not random smashing. It was a pre-planned, multi-step process that demonstrated abstract thought. It produced a diverse toolkit of points for spears and specialized scrapers for processing hides. When Homo sapiens arrived in Ice Age Europe, they brought with them an even more advanced technology based on the production of long, slender blades. Using a technique called indirect percussion, they could strike off dozens of standardized razor-sharp blades from a single core. This was manufacturing on an unprecedented scale, an efficient system for mass-producing the building blocks of their technology. These blades were then fashioned into an array of specialized tools: knives for butchering, spear points for hunting, and burins, fine-pointed chisels, for intricate work on other materials. This innovation opened up a new world of possibilities. Bone, antler, and ivory, previously too difficult to shape, now became primary materials. The invention of the bone needle, a tiny but transformative tool, allowed for the sewing of tailored clothing, offering far superior protection from the cold than simple draped hides. Perhaps the most significant invention was the spear thrower, or atlatl. This device acted as a lever, dramatically increasing the range, speed, and penetrating power of a spear. It allowed hunters to attack dangerous megafauna from a safer distance, fundamentally changing the balance of power between humans and their prey. But the ultimate tool was fire. The ability to control and create fire on demand was a watershed moment. Fire provided warmth in the lethal cold, kept nocturnal predators at bay, and transformed the night into a time for social bonding and storytelling. It cooked food, neutralizing pathogens and unlocking nutrients, which may have fueled the development of our energy-hungry brains. Fire was more than a tool. It was a portable piece of the sun, a beacon of human ingenuity in the heart of the ice. With this expanding arsenal of technology, humans were no longer just reacting to their environment. They were actively shaping their destiny, becoming the most adaptable and formidable creatures of the Ice Age. The defining landscape of the Ice Age was not, as is often imagined, an endless sheet of barren ice. For much of the northern hemisphere, it was a lost world, an ecosystem that no longer exists today. This was the Mammoth Steppe, the largest biome on the planet. Stretching from the Iberian Peninsula across the vast breadth of Eurasia and over the Bering Land Bridge into North America, it was a world dominated by grass. It was a cold, arid environment, with precipitation locked away in the great ice sheets. The dry air and persistent winds prevented the accumulation of deep snow, allowing sunlight to reach the ground. This created not a barren tundra, but an immensely productive grassland. Unlike modern tundra, which is dominated by mosses and lichens, the mammoth steppe was a rich pasture of nutritious grasses, herbs, and flowering forbs. The permafrost below acted as a reservoir, trapping moisture that nourished plant roots during the short, intense growing season of the summer. This vegetation was the engine that powered the entire ecosystem. It supported a biomass of animal life that rivals, and perhaps even exceeded, the modern Serengeti. This was the heartland of the megafauna. Vast herds of woolly mammoths, woolly rhinos, steppe bison, horses, and reindeer roamed these plains in numbers almost impossible to comprehend. Their constant grazing and trampling played a crucial role in maintaining the ecosystem. By clearing away old growth, disturbing the soil, and fertilizing it with their waste, they prevented the encroachment of forests and promoted the growth of the very grasses they depended on. The giants were the gardeners of their own world. For the Paleolithic humans who lived there, the mammoth steppe was a landscape of immense opportunity. The open terrain was ideal for tracking the great herds, and the sheer abundance of animals provided a reliable and concentrated source of food and raw materials. Life revolved around the migrations of these animals. Human hunters were an integral part of this ecosystem, a new and highly intelligent predator in a world of giants. For tens of thousands of years, this dynamic equilibrium held. The steppe, the grazers, and the hunters existed in a stable, interconnected web. It seemed a permanent world, a kingdom of grass and giants that would last forever. But the planetary climate system that had created this world was beginning to shift. The ice was stirring, and a great thaw was on the horizon, a change that would unravel the mammoth steppe and bring its reign to a sudden, dramatic end. As the grip of the ice tightened across the northern hemisphere, it performed an act of geologic alchemy. By locking away unfathomable volumes of water into continent-sized glaciers, it lowered the planet's oceans by more than 100 meters. In the far north, this great subtraction revealed a world that had been hidden beneath the waves. A vast, subcontinent-sized connection emerged between the easternmost tip of Siberia and the western edge of Alaska. This was not a narrow isthmus of ice, but a sprawling, habitable landscape known as Beringia. It stretched for over 1,000 miles from north to south, a cold, arid world, but one teeming with life. This was the mammoth steppe, an ecosystem that no longer exists on Earth. It was an immense grassland, swept by persistent winds that kept the snow cover thin, allowing hardy grasses and shrubs to thrive even in the profound cold. This vegetation supported colossal herds of Ice Age megafauna. Woolly mammoths, icons of the era, journeyed across the plains, alongside herds of steppe bison, wild horses, and caribou. They were pursued by a formidable array of predators: scimitar-toothed cats, giant short-faced bears, and packs of dire wolves. Into this challenging yet bountiful world stepped humanity. Following the great herds, small, resilient bands of hunter-gatherers ventured out of Asia and onto this new land. For thousands of years, Beringia was not a bridge to be crossed, but a homeland to be settled. Genetic evidence suggests these people, the ancestors of all native peoples of the Americas, lived in genetic isolation in this region for millennia. They honed their survival skills, perfecting their tools and their understanding of this unique environment. Then, as corridors began to open between the massive Laurentide and Cordilleran ice sheets covering North America, they pushed forward. The exact timing of their arrival remains a subject of intense scientific debate. For decades, the Clovis first model suggested the first arrivals occurred around 13,000 years ago. But mounting evidence from sites across both continents points to a much earlier, more complex story of settlement. What is certain is that this was one of the last great human migrations, a journey into a hemisphere entirely empty of people. They were not explorers in our sense of the word, but families moving into new hunting grounds, generation by generation, driven by necessity and opportunity. They carried with them the skills, ingenuity, and cultural memory that would allow them to populate 2 continents. The first steps onto the American continent marked the final chapter of humanity's global expansion, a testament to our species' incredible adaptability. They had crossed into a new world, but the true scale of the challenges and wonders that awaited them was yet to be revealed. While some groups of humans were pushing into new continents, others, deep in the heartlands of Ice Age Europe, were embarking on a different kind of journey, an exploration of the human mind. In the sheltered valleys of modern-day France and Spain, a cultural revolution was taking place. Inside the deep, silent darkness of limestone caves, the human spirit was finding a powerful new voice. This was the dawn of art. For thousands of years, our ancestors had been masters of survival, creating functional tools of stone, bone, and wood. But around 40,000 years ago, something changed. They began creating objects and images of extraordinary beauty and symbolic power. At sites like Chauvet, Lascaux, and Altamira, they navigated treacherous passages, crawling deep into the earth, carrying only the flickering light of tallow lamps. There, on the undulating stone canvases of the cave walls, they brought their world to life. Using natural pigments, black from charcoal, and a rich palette of reds, yellows, and browns from ground ochre, they painted and engraved breathtakingly realistic images of the animals that dominated their landscape. Powerful aurochs, graceful horses, herds of bison, and majestic stags gallop across the rock. The artists used the natural contours of the caves to give their creations a 3-dimensional quality, a sense of movement and vitality that is still palpable today. What drove them to create this art in such inaccessible places? The meaning remains one of history's greatest mysteries. Were these images part of shamanistic rituals, attempts to connect with the spirit world? Were they a form of hunting magic, meant to ensure a successful hunt? Or were they sophisticated records of tribal history and mythology, a way of passing knowledge through generations in a world without writing? Perhaps it was all of these things. The artistry was not confined to painting. This period saw an explosion of creativity in other forms. Skilled artisans carved intricate figurines from mammoth ivory and bone, including the famous Venus figures with their exaggerated features, thought to be symbols of fertility and life. They crafted delicate bone flutes, filling the cold Ice Age air with music. This was not the work of simple, primitive people. It was the expression of complex, abstract thought, of a species grappling with its place in the universe and developing a shared culture. These silent galleries, preserved for millennia, are a direct message from our deepest past. They are whispers across time, telling us that the fundamental human urge to create, to communicate, and to find meaning is as old as humanity itself. The creative flourishing of the Upper Paleolithic occurred against a backdrop of a planet growing ever colder. The Earth's orbital cycles, the gentle celestial rhythms that govern our climate, were aligning to plunge the world into its deepest freeze in over 100,000 years. This was the last glacial maximum, or LGM, a period that began around 26,000 years ago. It represents the absolute peak of the last ice age. The ice sheets, which had been growing for millennia, now reached their greatest extent. In North America, the colossal Laurentide ice sheet covered nearly all of Canada and stretched south past the Great Lakes, a wall of ice in some places more than 2 miles thick. In Europe, the Weichselian ice sheet blanketed Scandinavia and reached into Germany and Poland. Mountain glaciers expanded on a global scale, from the Andes to the Himalayas. So much of the world's water was now locked up in this ice that global sea levels fell to their lowest point, about 125 meters below where they are today. The world of the LGM was a harsh and fragmented place. The climate was not just colder, but significantly drier. Vast regions became polar deserts, inhospitable even to the hardiest Ice Age life. Forests retreated, and the mammoth steppe expanded, but life was concentrated into pockets of relative habitability known as refugia. For humanity, this was the ultimate test of endurance. Populations were pushed south into these refugia, in places like southern France, the Iberian Peninsula, and the plains of Ukraine. Survival demanded new levels of innovation. This period saw the development of more refined toolkits, including the invention of the needle, which allowed for the creation of sophisticated tailored clothing from animal hides, essential for surviving the brutal cold. Hunting strategies became more complex and communal, necessary for taking down the large, dangerous animals that provided the fat and protein needed to endure the long winters. Life was lived on the edge, a constant negotiation with a planet at its most severe. Every sunrise was a victory against the cold. Every successful hunt was a reprieve. The world was dominated by ice, a seemingly permanent and unchangeable reality. From the perspective of a person living at the time, it would have been impossible to imagine that this frozen state was not eternal. They lived in the shadow of glaciers that had defined their world for countless generations. But even as the ice reached its maximum extent, the subtle, inexorable forces of planetary mechanics were already plotting its demise. The deep freeze had reached its limit, and the long, slow process of reversal was about to begin. For thousands of years, the ice had been the undisputed ruler of the world, but its reign was coming to an end. The cause was not on Earth, but in the heavens. Subtle shifts in the planet's orbit and tilt, known as Milankovitch cycles, began to alter the amount of solar radiation reaching the northern hemisphere. The change was imperceptible at first, a slightly warmer summer, a little less winter snowfall. But over centuries, the effect compounded. The great planetary heat engine was slowly shifting into reverse. The thaw had begun. Around 15,000 years ago, the warming accelerated dramatically. Glaciers that had been stable for millennia began to groan, crack, and retreat. This was not a gentle, peaceful melting. It was a chaotic and violent process. As the ice melted, it formed enormous lakes at the edges of the glaciers, bodies of water larger than any that exist today, held back only by precarious dams of ice or rock. When these dams inevitably failed, the results were cataclysmic. In North America, the periodic collapse of the ice dam holding back glacial Lake Missoula unleashed biblical-scale floods. A wall of water hundreds of feet high, carrying more volume than all the world's rivers combined, would roar across the landscape of the Pacific Northwest, scouring the land down to bedrock in a matter of days. This violent reshaping was mirrored across the world, as meltwater carved new river valleys and landscapes. Life responded to the warmth. Tundra gave way to advancing forests of birch and pine. Animals and humans began to move back into lands that had been locked under ice for an eternity. But the planet's climate system, thrown out of balance, was prone to violent swings. Around 12,900 years ago, the warming trend stopped and suddenly reversed. In a period of perhaps only a few decades, temperatures in the northern hemisphere plummeted back to near-glacial conditions. This climatic shock, known as the Younger Dryas, lasted for over 1,000 years. It was likely caused by a massive influx of fresh meltwater into the North Atlantic, disrupting the ocean currents that transported heat around the globe. It was a final, brutal winter, a last gasp of the Ice Age that tested the resilience of the new ecosystems and the humans who depended on them. Then, just as suddenly as it began, the younger Dryas ended. The warming returned with a vengeance, and the final retreat of the great ice sheets began in earnest. The world was waking from its long, frozen slumber, but the planet that emerged would be utterly transformed. The final act of the Ice Age was not written in ice, but in water. The melting of the great glaciers released a staggering volume of water back into the world's oceans, initiating a period of sea level rise unparalleled in human history. Over several thousand years, the seas rose by more than 100 meters, fundamentally redrawing the map of the world. The consequences were profound. Low-lying coastal plains that had been fertile hunting grounds for generations were relentlessly submerged. The land bridge of Beringia, which had enabled the settlement of the Americas, vanished beneath the waves, creating the Bering Strait and separating the Old World from the New. In Europe, the rising waters flooded the basin between Britain and the continent. A vast, low-lying territory, known to us as Doggerland, which was once a heartland of human settlement, was slowly inundated. Its inhabitants were forced into a centuries-long retreat as their world disappeared, their story becoming a distant memory, preserved only in the artifacts occasionally dredged up by fishing nets. Britain was severed from mainland Europe, becoming the island it is today. Coastlines retreated globally, forcing human populations to adapt to new shorelines and new marine resources. This dramatic transformation of the physical world was accompanied by a biological one. The Mammoth Steppe, the vast cold grassland that had supported the Ice Age giants, disappeared. It was replaced by temperate forests and wetlands, environments to which the megafauna were not adapted. The woolly mammoth, the woolly rhinoceros, the saber-toothed cat, and the giant sloth found their habitats shrinking and fragmenting. This rapid environmental change, combined with the increasing pressure from highly efficient human hunters, proved to be a fatal combination. One by one, the iconic species of the Ice Age vanished from the Earth forever. This wave of extinctions marked the end of an entire ecological era. The world that emerged from the thaw was a warmer, wetter, and more stable one. The chaotic climate swings of the Pleistocene gave way to the relative calm of our current epoch, the Holocene. The ice was gone, the giants were gone, and the coastlines had settled into their modern configurations. Humanity had not only survived the immense challenges of the Ice Age, but had spread to every habitable continent on Earth. They now stood alone, the planet's undisputed dominant species, in a world remade by water. The stage was now set for the next great human experiment, the development of agriculture, the rise of cities, and the birth of civilization. For tens of thousands of years, they were the undisputed masters of the frozen world. Herds of woolly mammoths, their colossal forms dark against the endless white, navigated the glacial plains. Dire wolves, larger and more robust than their modern relatives, hunted in formidable packs. In the shadows lurked the Smilodon, the saber-toothed cat, a predator of terrifying efficiency. And across the Americas, the giant ground sloth, Megatherium, moved with a slow, deliberate power, browsing on treetops. These were the megafauna, the great beasts of the Pleistocene, perfectly adapted to the rigors of the Ice Age. Their reign seemed eternal, their dominion absolute. Yet, as the great ice sheets began their final, stuttering retreat, a profound silence started to fall across the land. One by one, these giants vanished from the face of the Earth. The question of their disappearance remains one of paleontology's most compelling and debated mysteries. Two primary narratives compete to explain this mass extinction. The first points to the very force that ended the Ice Age: climate change. As temperatures rose, the vast cold grasslands that sustained the massive herbivores began to shrink, replaced by expanding forests and wetlands. The mammoths' food source dwindled, and the entire food web that depended on them started to unravel. This environmental shift, while gradual on a human timescale, was a tectonic upheaval for species that had evolved over millennia for a specific, stable environment. The second theory introduces a new and uniquely disruptive force onto the landscape: modern humans. Spreading across continents, these small, intelligent primates were hunters of unprecedented skill. In North America, the arrival of the Clovis people, identified by their distinctive and beautifully crafted spear points, coincides almost perfectly with the rapid decline of the megafauna. Archaeological sites reveal these points lodged among the bones of mammoths, clear evidence of successful hunts. This overkill hypothesis suggests that relentless human predation pushed already stressed animal populations over the brink. Was it the changing climate or the hunter's spear? The truth is likely a complex interplay of both. A warming world weakened the giants, shrinking their habitats and food supplies. Into this vulnerable ecosystem stepped a new apex predator, armed with ingenuity and cooperative strategies. It was a perfect storm of environmental pressure and human impact. The giants, who had weathered the harshest cold the planet could offer, could not withstand the coming of the thaw and the rise of humanity. Their silent departure marked the end of an entire biological era, a world of titans now lost to time. But as their numbers dwindled, the planet was preparing one final, dramatic cold shock, an event that would seal the fate of any who remained. The Earth was warming. The colossal Laurentide and Scandinavian ice sheets were in retreat, pouring unimaginable volumes of fresh water into the oceans. Forests were advancing, reclaiming land that had been buried under ice for millennia. For humanity and the surviving fauna, it must have seemed like the dawn of a new, more benevolent age. But the planet's climate system, knocked out of its glacial equilibrium, was far from stable. It had one last, brutal surprise in store. Around 12,900 years ago, the warming trend stopped. Then, it violently reversed. In a matter of decades, perhaps even less, temperatures across the northern hemisphere plunged back to near-full glacial conditions. This was the Younger Dryas, a geologically brief but intensely cold period that lasted for over 1,000 years. It was a planetary deep freeze, a final, biting winter before the true spring of our modern era. The evidence for this sudden cold snap is etched into the geological record worldwide. Pollen analysis shows the return of cold-adapted shrubs and grasses to areas where forests had just taken root. Ice cores from Greenland reveal a dramatic drop in temperature and an increase in atmospheric dust, signaling colder, windier conditions. For years, the cause was a profound puzzle. Today, the leading theory focuses on the plumbing of the planet. As the Laurentide ice sheet melted, it created an immense freshwater body in North America known as Lake Agassiz, larger than all the modern Great Lakes combined. Scientists believe the ice dam holding this lake in place catastrophically failed. A torrent of cold, fresh water, greater than the flow of all the world's rivers today, surged into the North Atlantic Ocean. This massive influx of fresh water was less dense than the salty ocean water, and it effectively shut down the Atlantic's great conveyor belt, the thermohaline circulation that brings warm water from the tropics northward. The heat pump for the northern hemisphere was switched off. The consequences were immediate and severe. The cold returned with a vengeance, putting immense stress on ecosystems and early human societies. The few remaining megafauna, already struggling in a changing world, now faced a return to the harsh conditions their ancestors endured. For human populations like the Clovis culture in North America, this climatic whiplash would have been devastating, forcing radical adaptation to survive. The Younger Dryas stands as a stark reminder of the planet's capacity for abrupt, high-impact change. It shows that the transition out of an ice age is not a smooth, linear process, but a volatile and unpredictable journey, filled with climatic tipping points. This final frost was the last gasp of the Old World, 1,000-year winter before the planet finally settled into the warmth of the Holocene. The ice is gone, but its memory is everywhere. It is written not in books, but in the very shape of the land we inhabit. The Pleistocene ice sheets were not static features. They were dynamic rivers of ice, flowing under their own immense weight. They were the most powerful erosional force the planet has seen in millions of years, acting as continental-scale bulldozers and sculptors. As they advanced, they scraped the landscape bare, plucking boulders the size of houses and grinding mountains down to their roots. When they retreated, they left behind a transformed world, a geography fundamentally reshaped by their passage. Look at a map of North America, and you will see their most magnificent creation, the Great Lakes. These inland seas were gouged out of the earth by the lobes of the Laurentide ice sheet, which exploited pre-existing river valleys and softer rock, carving deep basins that filled with meltwater as the ice receded. Across the globe, from the Alps to the Rockies, we see the classic signature of glacial carving in the form of U-shaped valleys. Where a river carves a V-shape, a glacier fills a valley from wall to wall, grinding it into a deep, flat-bottomed trough with steep sides. The iconic fjords of Norway, New Zealand, and Chile are these same U-shaped valleys, carved so deeply by coastal glaciers that they were flooded by the rising sea as the Ice Age ended. The glaciers were not just carvers, they were also builders. As the ice melted, it dropped the vast load of rock and sediment it carried. This material, known as glacial till, was deposited in distinctive landforms. Long, winding ridges called moraines mark the places where the glaciers paused their retreat, piling up debris like a conveyor belt. Elongated, teardrop-shaped hills called drumlins were molded under the moving ice, their orientation still pointing in the direction of the ancient flow. And sinuous ridges of sand and gravel, called eskers, trace the paths of meltwater rivers that once flowed in tunnels at the base of the ice. Even the land itself is still recovering. The weight of ice sheets miles thick depressed the Earth's crust. As that weight was lifted, the land began to slowly rise in a process called isostatic rebound. Parts of Scandinavia and Canada are still rising today, centimeters per year, still breathing a slow sigh of relief after their long frozen burden was removed. From the Great Lakes to the smallest scratches on a bedrock outcrop, the Ice Age left an indelible imprint. It is a physical legacy that dictates where our rivers flow, where our lakes form, and where our cities are built. To truly understand the rhythm of the Ice Age, we must travel to the coldest, most desolate places on Earth, the great ice sheets of Greenland and Antarctica. Here, buried under miles of compressed snow, lies a perfect frozen archive of Earth's past climate. This library of ice is accessible through one of modern science's most remarkable achievements, ice core drilling. For decades, international teams of scientists have endured extreme conditions to drill deep into the heart of these ice sheets, extracting cylinders of ice that are, in essence, frozen time capsules. Each layer of an ice core represents a year's snowfall. In the summer, lighter, fluffier snow falls. In the winter, the snow is denser. These alternating layers, like the rings of a tree, allow scientists to count back through time, year by year, for hundreds of thousands of years. But the real treasure lies trapped within the ice itself. As snow falls, it traps tiny pockets of the surrounding air. As the snow is compressed into ice, these pockets are sealed, preserving perfect, pristine samples of Earth's ancient atmosphere. Using sophisticated lab techniques, scientists can drill into these bubbles and measure the exact composition of the air from the distant past. They can track the rise and fall of greenhouse gases, like carbon dioxide and methane, with astonishing precision, creating a detailed graph of their concentrations stretching back nearly 1 million years. This data provides irrefutable proof of the link between greenhouse gases and planetary temperature. The ice itself holds another secret. The water molecules within it contain different isotopes of oxygen and hydrogen. The ratio of these heavier and lighter isotopes is directly related to the temperature at the time the snow fell. By analyzing this ratio layer by layer, scientists can construct a precise thermometer of the past, charting the dramatic temperature swings between glacial and interglacial periods. The cores also reveal a history of major global events. A dark band of dust might indicate a massive volcanic eruption thousands of miles away, or a period of extended drought that created vast dust storms. This frozen record, obtained from projects like Vostok Station in Antarctica and the Greenland Ice Core project, has revolutionized our understanding of Earth's climate system. It has shown us the natural cycles that drive the ice ages and the speed at which climate can change. It is a detailed, unambiguous message from the past, a warning and a guide written in the language of ice and air. The world of towering ice sheets and roaming mammoths may seem like a distant, alien planet, but the forces that govern that world are the same ones that govern ours today. The story of the Ice Age is not a closed chapter of history. It is the essential backstory to our present moment, and it holds profound implications for our future. We now understand that the great pulse of the Ice Ages is driven by subtle, predictable changes in Earth's orbit around the Sun, known as Milankovitch cycles. These cycles alter the amount and distribution of solar energy reaching the planet, acting as a pacemaker for the advance and retreat of ice over tens of thousands of years. They are the slow, steady heartbeat of the global climate system. For millennia, Earth's climate has danced to this celestial rhythm. The ice cores provide a perfect record of this dance, showing how temperature and atmospheric carbon dioxide have moved in near-perfect synchrony. When the planet warmed, carbon dioxide levels rose. When it cooled, they fell. This natural cycle operated within a well-defined range, but the end of that record tells a new and alarming story. In the last century, the concentration of carbon dioxide in the atmosphere has skyrocketed, leaving the natural range of the ice ages far behind. The speed of this change is what is so unprecedented. The warming that ended the last glacial period, a dramatic global transformation, saw carbon dioxide rise by about 80 parts per million over several thousand years. Humanity has caused a much larger increase in a tiny fraction of that time. We are no longer observing the natural rhythm. We are now the primary driver of the climate system. The echoes of the Ice Age serve as a critical warning. We know from the past that the great ice sheets of Greenland and Antarctica, the last remnants of that frozen world, are sensitive to warming. Their melting would lead to catastrophic sea level rise. We know that the ocean currents that regulate our climate can be disrupted, as they were during the Younger Dryas, leading to abrupt and unpredictable shifts. The Ice Age provides the ultimate context for our modern world. It has shown us how interconnected the planet's systems are, from the atmosphere to the oceans to the ice. It has given us the scientific tools, through the study of its frozen legacies, to understand the delicate balance of our climate. The frozen planet of the past speaks to us with a clear voice, reminding us that we live on a world capable of profound transformation. The question it leaves for us is not whether the climate will change, but how we will respond to the changes we are now driving.